There's something happening in our universe, something subtle, something quiet, but deeply wrong. Not broken, not collapsing, but inconsistent. And the strangest part is this: the more precisely we measure reality, the less it agrees with itself. Right now, two of the most advanced methods humanity has ever created are looking at the same universe and telling us two completely different stories. Not slightly different, not close, but fundamentally incompatible. One says the universe is expanding at one speed, the other says it's expanding faster, and the gap between them is no longer small enough to ignore. So here's the question that keeps physicists awake at night. What if the problem isn't the measurement, but reality itself? Because if that's true, and then everything we think we know about the universe, its age, its size, its history, could be incomplete, or worse, misleading. And this isn't speculation. This comes from scientists who have spent their entire lives measuring the cosmos with extreme precision. People who don't say things like this lightly. One of them put it simply: we may have misunderstood the universe. Pause for a moment and let that sink in. Not a small correction, not a minor adjustment, but something deeper. Because when your most trusted model, the one that explains how everything works, starts to crack, you don't just fix a number, you start asking new questions. And those questions can change everything. But before we go deeper, if you enjoy exploring ideas like this, the kind that slowly reshape how you see reality, take a moment to like the video and subscribe. Not because you have to, but because this kind of thinking, it stays with you. Now, let's go further. For nearly a century, modern cosmology has been built on something called the Standard Model of the universe. It's elegant, predictive, surprisingly accurate. It tells us how the universe began, how it expanded, how galaxies formed, and why everything around us looks the way it does. And for decades, it worked almost perfectly. Observation after observation, prediction after prediction, everything lined up. Too well, some might say, because when a theory explains everything, you stop questioning it until something doesn't fit. At first, it was easy to dismiss small discrepancies, tiny mismatches in data, maybe just noise, maybe measurement error, but they didn't go away. They became clearer, sharper, more consistent, and eventually impossible to ignore. That's when scientists realized something unsettling. This wasn't noise. This was a signal, a crack in the model. And that crack has a name: the Hubble tension. Now, don't let the name fool you. This isn't just a technical detail. This is a number that controls how fast the universe is expanding right now. Not billions of years ago, not in theory, right now. And if that number changes, everything changes. The age of the universe shifts. The timeline of galaxies moves. The story of cosmic evolution rewrites itself. It's like adjusting a single dial and watching the entire history of reality rearrange. So you would expect something like this to be measured carefully, and it has been, again and again and again, using different methods, different instruments, different assumptions. But here's where things get strange. No matter how carefully we measure it, we keep getting two different answers. One from the early universe, one from the present universe. Both precise, both consistent, and both in disagreement. This is the first mystery. If our best measurements don't agree, which one is wrong? Or more unsettling? What if neither of them is? What if the universe is more complicated than the model we built to describe it? And that leads to a second question, one that is even harder to ignore. What if this is not just one problem, but the first sign of something deeper? Because as scientists began to look closer, to test this tension more carefully, they noticed something else, something unexpected, something that didn't just challenge one number, but the entire timeline of the universe. Galaxies appearing far too early, fully formed, when the universe should have still been chaotic, too big, too structured, too soon. And suddenly, the question changed. This is the second mystery. How did the universe build complexity so quickly? And beneath both of these, there is a third question quietly waiting. Because if expansion is misunderstood and structure formed too early, then something deeper must be influencing both. Something we haven't fully grasped yet. And that brings us to the third mystery. What is really driving the evolution of the universe? 3 questions, all connected, all unresolved, and none of them fully explained. But this is where things begin to get interesting, because sometimes, when reality stops making sense, it's not because we've reached the end of understanding. It's because we're standing at the beginning of a new one. And in the next part, we're going to follow that first crack a little deeper, because it doesn't stop with expansion. It leads to something even more difficult to explain, something that shouldn't exist at all, and yet it does. Something that shouldn't exist at all. Because when scientists turned their most powerful telescopes toward the early universe, they expected to see something simple: chaotic gas, faint light, small structures, just beginning to form, a universe still in its infancy. But that's not what they found. Instead, they saw galaxies. Not small ones, not incomplete ones, but massive, bright, fully formed galaxy, appearing far earlier than they should. And this is where things begin to feel impossible. Because according to everything we understand, galaxies take time, a long time. Matter has to gather, gas has to cool, stars have to ignite, structures have to grow. It's a slow process, step by step, layer by layer, like building a city. You don't get skyscrapers overnight. You start with foundations, then small structures, then, over time, complexity emerges. But what we're seeing looks more like the city was already there. Lights on, structures complete, no visible construction history. And that leads to a question that no one expected to ask. How did the universe build so much, so quickly? This is the second mystery, becoming impossible to ignore. Now at first, scientists assumed there must be a mistake. Because when observations don't match theory, the safest assumption is that something in the measurement is wrong. Maybe these galaxies only appear massive. Maybe something is distorting the light. Maybe we're misinterpreting what we see. Because when you look billions of light years away, you're not seeing objects directly. You're seeing ancient light, light that has traveled for billions of years before reaching us. And along the way, it can be stretched, distorted, amplified. So the first step was simple: check the data, and then check it again. But the results didn't disappear. They became clearer, more consistent, and harder to explain. That's when scientists started looking deeper, not just at the galaxies themselves, but at what might be happening inside them. And what they found added another layer to the mystery. At the center of many of these early galaxies, there were black holes, not ordinary ones, but enormous, actively feeding black holes, pulling in matter, heating it to extreme temperatures, and releasing huge amounts of energy. From a distance, that energy makes the galaxy appear brighter, more massive, more developed, like shining a spotlight on through the center of a structure and mistaking it for something larger. So, when scientists accounted for this, some galaxies became less extreme. Not as massive as they first appeared. But here's the problem. Not all of them. Even after correcting for these effects, too many galaxies remained. Too large, too early, too structured, enough to keep the mystery alive. And now, the question becomes more precise. If these galaxies are real, what allowed them to form so quickly? Because under normal physics, they shouldn't have had enough time. Gravity needs time. Stars take time to form. Gas takes time to collapse and ignite. And yet, these galaxies seem to have bypassed that timeline, as if the universe moved faster in its earliest moments. Now pause here, because this connects back to the first mystery, the expansion problem. If the universe expanded differently in the past, then structure would form differently too. Faster expansion, slower collapse, slower expansion, faster structure formation. And suddenly, these two mysteries don't feel separate anymore. They begin to overlap, which leads to a deeper question. What if something about the early universe was fundamentally different from what we assume today? Now, there are a few possibilities. Some scientists suggest that the early universe was simply denser, hotter, more efficient at forming stars. In those conditions, gas could collapse faster, structures could grow more quickly, not breaking physics, but pushing it to its limits. Others suggest something more radical. What if there were unknown particles or forces present in the early universe that no longer exist today? Something that gave structure formation in a temporary boost, a kind of cosmic shortcut, and then disappeared. Now that idea might sound extreme, but it introduces something important. The possibility that the laws of physics are not constant across time, that they may evolve. And if that's true, then what we observe today is only part of the story. Now, let's step back for a moment. We have two major mysteries. The universe expands in ways that don't agree, and galaxies form earlier than they should, both precise, both repeated, both unexplained, and both pointing in the same direction, towards something missing in our understanding of reality. But just when it seems like things couldn't get more complicated, they do. Because the structure of these early galaxies isn't just surprising in size, it's surprising in behavior. Some of them appear unexpectedly organized, smooth, rotating, stable, as if they've already matured, while others from the same time period look chaotic, clumpy, unstable, both existing side by side, order and disorder appearing together far earlier than expected. And that creates a third layer of tension, not just how galaxies form, but how structure itself emerges. Why does the universe allow both extremes at the same time? Why do some systems evolve rapidly into order while others remain chaotic? Is it environment, chance, or something deeper built into the fabric of reality? And now, we're no longer just asking about galaxies. We're asking about the rules themselves. Because whatever is causing this doesn't just affect structure. It may also affect expansion. And possibly everything in between. And in the next part, we're going to follow that connection. Because beneath all of this, there may be a single hidden factor, one we've already named, but never truly understood: dark energy. And if that idea is even slightly wrong, then everything we've seen so far might just be the beginning. Dark energy. We gave it a name, but not an explanation, because dark energy isn't something we've seen, not directly. We don't know what it's made of, we don't know where it comes from, and we don't know why it exists. And yet, we are certain it's there, because without it, the universe we observe would not behave the way it does. This is where things start to feel strange. In the late 1990s, astronomers made a discovery that changed everything. They were measuring distant supernovae, trying to understand how the universe expands, and they expected something simple. They expected gravity to slow everything down. Galaxies pulling on each other, matter resisting expansion. A gradual deceleration. But that's not what they saw. The expansion wasn't slowing down. It was accelerating. Faster and faster. As if something was pushing the universe apart, not violently, but persistently. And whatever that something was, it had to be everywhere. Not just in galaxies, not just in clusters, but in the empty space between them. So, they gave it a name: dark energy. Now, here's where it connects to everything we've been exploring. If dark energy controls expansion, then any misunderstanding of it would directly affect the Hubble tension. Which means the first mystery might not be about measurements at all. It might be about this invisible, unknown, dominant component of the universe. Because here's the part most people don't realize: dark energy makes up about 70% of the entire universe. Everything we see, stars, planets, galaxies, is less than 5%. The rest is something we don't understand. Now, pause for a moment, because this changes the perspective completely. We are not studying a universe we understand with a few missing details. We are studying a universe where most of it is unknown, and we're trying to explain it using models built from the smallest visible fraction. Now, there is a simple explanation for dark energy. It's called vacuum energy. The idea that empty space is not truly empty, that even in complete darkness there is energy, and as the universe expands, more space appears, which means more energy appears with it, and that energy pushes everything apart. It's elegant, simple, and possibly wrong, because when scientists try to calculate how much energy should exist in empty space, the numbers don't match. Not even close. They're off by a factor so large it's almost impossible to comprehend. Like predicting the weight of a car and ending up with the mass of a galaxy. That's not a small error. That's a fundamental disconnect. So now we have a strange situation. We rely on dark energy to explain the expansion of the universe, but we can't explain dark energy itself. And if that wasn't enough, there's another twist. Some recent observations suggest that dark energy might not be constant. It might change over time. And if that's true, then everything becomes unstable. Because the standard model assumes that dark energy is fixed, a constant background force. But if it evolves, then the entire timeline of the universe has to be reconsidered. Now, think about what that means. If dark energy behaved differently in the early universe, then expansion would be different. And if expansion was different, then structure formation would be different. And suddenly, the second mystery, early galaxies, starts to make sense. Faster structure formation under different conditions, and the first mystery. The Hubble tension also begins to connect. Predictions from the early universe no longer matching what we observe today. Two problems, one possible cause. But this comes with a cost. Because if dark energy changes, then the equations we trust are incomplete. Not slightly wrong, but missing something fundamental. And that leads to a deeper realization. We are not just missing a piece of the puzzle. We might be using the wrong puzzle entirely. Now, let's pause again. We have three major questions now. Why does expansion disagree? How did galaxies form so early? What is dark energy? And now they are starting to converge. But just as this picture begins to form, another anomaly appears. Less known, less discussed, but just as important. It's called the S8 tension. And unlike the Hubble tension, which deals with expansion, this one deals with structure. Specifically, how matter is distributed across the universe. According to our best models, matter should cluster together in a certain way, a predictable pattern. But when we measure it, we find something slightly different. The universe is less clumpy than expected, not dramatically, but consistently. And consistency is what makes it important, because random errors don't repeat themselves this precisely. This is another signal, another crack. And here's where things get interesting. Some scientists believe the Hubble tension and the S8 tension might be connected. Two symptoms of the same underlying problem, like seeing cracks in a wall and realizing they both trace back to the foundation. Now imagine that, not one issue, but a structural shift in how the universe behaves, and that leads to a new possibility. There may be something hidden in the universe, not something we've directly detected, but something that influences both expansion and structure formation, subtle but persistent. And if that's true, then what we're seeing right now is not confusion, it's a signal, a sign that our understanding is about to change. And in the next part, we're going to explore something even more unsettling. Because if these tensions are real, then we have to consider a possibility. That sounds almost impossible. What if the laws of physics themselves are not fixed? What if they change over time? And if they do, what does that mean for everything we think is real? What if the laws of the universe are not fixed? Not constant, not permanent, but changing, slowly, quietly, over time. At first, that idea feels impossible, because modern physics is built on constants, the speed of light, the strength of gravity, the charge of an electron. These are supposed to be unchanging. They are the rules. But what if they're not? What if they're more like conditions, and conditions can evolve? Now pause here. Because if this is true, then everything we've assumed about the universe becomes context dependent. Not wrong, but incomplete. Let's imagine something simple. You're watching a game, but only from the second half. You study the patterns, you analyze the rules, you make predictions, and everything seems consistent. But what you don't realize is that the rules were different in the first half. Suddenly, your model still works, but only for part of the game. That's one way to think about the universe. What if the physics we observe today is only the late-time version of reality? And in the early universe, the rules were slightly different, not dramatically, just enough to change outcomes over billions of years. Now connect this back to what we've already seen, galaxies forming too early. If gravity behaved differently, even slightly stronger, structures could form faster. The expansion tension. If the properties of space changed over time, then predictions from the early universe would no longer match what we observe today. And dark energy. Maybe it's not a thing at all. Maybe it's a symptom of changing physics. Now, here's where things get even more interesting. Some physicists have proposed that certain constants might not be constant everywhere. They could vary across space, meaning different regions of the universe might follow slightly different rules. Imagine that. A universe where physics is not uniform, where one region behaves one way and another behaves differently, subtly, almost invisibly, but enough to create measurable effects. If that's true, then what we call tensions might not be errors. They might be boundaries, transitions between different regimes of reality. Now, think about that for a moment. Instead of one clean, universal model, we may be dealing with layers, zones, different phases of the same universe, and we just happen to exist in one of them. Now, we're no longer just talking about cosmology. We're asking something deeper. Are the laws of physics fundamental or emergent? Do they exist independently of the universe, or do they arise from it? Because if laws are emergent, then they can change. And if they change, then the universe has a history, not just of matter, but of rules, a timeline, not just of events, but of behavior itself. Now let's bring everything together again. We have an expanding universe that doesn't agree with itself. We have galaxies forming faster than expected. We have structure that doesn't quite match predictions, and we have a force, dark energy that we can't explain. What if these are not separate problems? What if they are all consequences of one deeper shift? A shift in the underlying rules. Now this is where some of the most radical ideas begin to appear. One idea suggests that the universe may have gone through different phases of physics, like water turning into ice, same substance, different behavior. In the earliest moments after the Big Bang, the universe was in an extreme state, hot, dense, highly energetic. Under those conditions, the rules we know today may not have applied. As the universe expanded and cooled, those rules settled into place, stabilized, but maybe not completely. Maybe small traces of that earlier phase still influence what we see today, echoes of a different version of reality. Now, here's another possibility. What if space itself is not passive, not just a stage where things happen, but something active, something that can change over time. If that's true, then expansion isn't just something happening in space. It's something happening to space. And if space evolves, then so does everything inside it. That includes motion, energy, structure, and the laws that describe them. Now, this might sound abstract. So imagine something simpler, a stretched fabric. At first, it's tight, rigid, but over time it loosens, softens. Objects placed on it behave differently depending on its tension. That's one way to think about space-time. And if its tension changes, then the behavior of the universe changes with it, gradually, subtly, but enough to create the discrepancies we observe. Now here's the key point. None of these ideas have been proven, but they all share something important. They take the anomalies seriously. They don't ignore them. They follow them. Because in physics, anomalies are often where breakthroughs begin. And right now, we are surrounded by them. So let's return again to our questions. Why does expansion disagree? How did galaxies form so early? What is dark energy? And now a fourth question joins them. Keys, are the laws of physics themselves changing? We don't have the answer yet, but something is becoming clear. These mysteries are not isolated, they are connected. And in the next part, we're going to explore one of the boldest ideas yet, an idea that doesn't just change the laws, but changes the stage itself. Because some scientists are beginning to consider that our universe might not be the only one. And if that's true, then everything we've been trying to explain might only be part of a much larger picture, a multiverse. And if we are inside it, then the question is no longer, what are the laws of the universe? But why these laws and not others? What if our universe is not the only one? Not metaphorically, not as an idea, but physically real. Because up until now, we've been trying to fix the universe, adjust the model, refine the measurements, explain the inconsistencies. But what if the problem is not inside the universe at all? What if it's the assumption that there is only one? This is the idea of the multiverse. And at first, it sounds like science fiction. Multiple universes, different laws, endless variations of reality. But here's the surprising part. The multiverse isn't just imagination. It emerges naturally from some of our best theories. Not because we want it to, but because the math allows it. Sometimes even requires it. Let's start with something familiar. The Big Bang. We often think of it as the beginning of everything, a single moment, a single universe. But some models suggest it may not have been unique. Instead, it could be one event, among many, one bubble, in a much larger structure. Imagine boiling water. Bubbles form, expand, collide, disappear. Each bubble is separate. Each has its own boundary, its own internal conditions. Now imagine, each bubble is a universe with its own version of physics. That's one way to visualize the multiverse. And if that's true, then our universe is just one realization of many possibilities. Now pause here, because this changes the question completely. Instead of asking, why does the universe have these laws? We ask, why does this universe have these laws? And the answer might be simple, because others don't. This is sometimes called selection. The idea that we observe this universe because it allows observers to exist, not because it's special, but because it's compatible with us. Now connect this back to the mysteries we've been following. The expansion problem. What if different universes expand at different rates? The early galaxies. What if structure forms differently depending on the universe? Dark energy. What if it behaves differently or doesn't exist at all in other universes? And suddenly, these problems don't look like contradictions anymore. They look like variations. Now, here's where things get more subtle. The multiverse doesn't solve everything. It explains diversity, but not mechanism. It tells us why different outcomes can exist, but not how they are generated. So the deeper question becomes, what creates these universes? And that leads to one of the most fascinating ideas in modern physics, eternal inflation. In this model, the early universe didn't just expand, it expanded incredibly fast, faster than the speed of light. And in some regions, that expansion never stopped. It continues, even now, creating new regions of space over and over again. And within those regions, new universes can form, each one branching off with its own conditions, its own constants, its own history. If this is true, then the multiverse is not rare, it's inevitable. Now, think about what that means. Somewhere, there could be a universe where gravity is stronger, where stars burn faster, where galaxies never form or form too quickly, or where expansion behaves differently, and somewhere else, a universe where dark energy is weaker or stronger or absent entirely. And suddenly, our universe stops being the default. It becomes one possibility among many. Now, here's where this connects directly back to the Hubble tension. If we are observing the universe from within one region with specific conditions, then our measurements may not represent the whole picture. They may reflect local behavior, not universal truth, meaning the disagreement we see is not a contradiction. It's a clue, a hint that we are only seeing part of something larger. Now, let's return again to our core questions. Why does expansion disagree? Maybe because we're comparing local observations to global assumptions. How did galaxies form so early? Maybe because our universe allows faster structure formation. What is dark energy? Maybe it's not a single phenomenon, but one of many possible behaviors. And now a deeper question emerges. Are we interpreting universal laws through a local lens? Because if we are, then every model we build has limits. Not wrong, but incomplete. Now, at this point, this might feel abstract, distant, but here's the grounding idea. Physics doesn't invent these possibilities. It discovers them. Through equations, through observations, through contradictions. The multiverse isn't a convenient escape. It's what happens when we take our theories seriously, even when they lead somewhere uncomfortable. Now let's step back again. We started with a simple mismatch, a number that didn't agree with itself, and now we're here, questioning whether our universe is just one part of something much larger. That's how far this path leads. And yet, Even this doesn't answer the deepest question, because even if there are many universes, we still don't know why any of them exist at all. And in the next part, we're going to move even deeper, beyond universes, beyond laws, into something more fundamental. Because some physicists are beginning to ask a question that sounds almost impossible. What if reality itself is not fundamental? What if everything we see emerges from something deeper that we don't yet understand? And if that's true, then everything we've explored so far might just be the surface. What if reality is not fundamental, not built from particles, not built from space, not even built from time, but from something deeper, something we don't directly see? Because for a long time, we believed the universe was made of things, atoms, particles, tiny building blocks that combine to form everything. But the deeper we look, the less solid those things become. Particles behave like waves, waves behave like probabilities. And at the smallest scales, reality stops looking like objects and starts looking like patterns, relationships, connections. Now, pause here, because this changes something fundamental. What if the universe is not made of things, but of information? Not objects, but interactions? Now, think about a digital image. Up close, it's just pixels, but arranged in the right way, it becomes something meaningful, a face, a landscape, a moment. The image doesn't exist separately. It emerges from the pattern. Now imagine reality works the same way. Space, time, matter, energy, all emerging from something more fundamental. Something like a deeper structure or a hidden code. Now, here's where this connects to everything we've seen so far. If reality is emergent, then the laws of physics might be emergent too. Not fixed rules, but patterns that arise from deeper behavior. And if that's true, then those patterns can change, evolve, which brings us back to the idea we touched earlier. What if the laws of physics are not constant in an emergent universe? They wouldn't have to be. They would depend on the underlying system, and that system might still be evolving. Now, let's connect this again to the mysteries we've been following. The expansion tension. Maybe it's not a contradiction, but a shift in how the system behaves. The early galaxies, maybe they formed quickly because the underlying structure allowed it. Dark energy, maybe it's not a force at all, but a byproduct of how space emerges. And suddenly, all three mysteries point in the same direction, not toward new particles, but toward a deeper layer of reality. Now, here's where things become even more interesting. Some physicists believe that space itself is not fundamental, that it emerges from something called entanglement, a quantum connection between particles, where two objects are linked in such a way that they no longer behave independently. Change one, and the other responds instantly, even across vast distances. Now imagine that on a cosmic scale, a network of connections, a hidden web linking everything together. And from that web, space itself appears. Distance is no longer fundamental. It's just a measure of how strongly things are connected. Strong connection feels close, and weak connection or feels far away. That's a completely different way of thinking about reality, not as a stage, but as a network. And if that network changes, then space changes, which means expansion might not be objects moving apart, but connections stretching, weakening, rearranging. Now think about what that implies. The expansion of the universe could be a transformation of relationships, not motion through space. And dark energy could be a reflection of how that network evolves, not a force, but a property of the system itself. Now let's return again to our questions. Why does expansion disagree? Because we may be measuring different aspects of an evolving system. How did galaxies form so early? Because the underlying structure allowed faster organization. What is dark energy? Possibly a feature of how reality emerges. And now a deeper question appears. What is the universe made of at the most fundamental level? If it's not matter and not space, then what is it? Some suggest information, others suggest mathematics, and some suggest something even more abstract. That reality is defined not by what things are, but by how they relate. Now, this might feel distant from observation, but it's not. Because these ideas are being tested through experiments, through simulations, through precise measurements of the cosmos, looking for patterns, looking for inconsistencies, looking for signs. That space is not what it seems. And interestingly, some of the anomalies we've already seen might be exactly those signs, small mismatches, subtle deviations, clues that something deeper is at play. Now let's step back again. We began with a simple tension, a disagreement in expansion. Then we found galaxies that shouldn't exist. Then we questioned dark energy, then the laws of physics, then the possibility of multiple universes. And now we're questioning reality itself. This is where the third loop goes deepest. Not just what is happening in the universe, but what is the universe really? And here's the strange part. The deeper we go, the less solid everything becomes. Less like objects, more like processes, more like patterns that are still unfolding. And that leads to something new. Because if reality is emergent, then it may not be complete. It may still be forming, still evolving. Which raises a new possibility. What if the universe is not finished, not static, but still becoming? And if that's true, then the anomalies we see today might not be errors. They might be transitions, moments where the system is changing, adapting. And in the next part, we're going to explore what that means for the future of the universe. Because if reality is still evolving, then the ending of the universe might not be what we expect, not fixed, not inevitable, but something far more uncertain and far more interesting. What if the future of the universe is not fixed, not predetermined, not inevitable, but still unfolding? For a long time, cosmology seemed to offer a clear answer. The universe expands. Dark energy pushes everything apart. Galaxies drift away. Stars burn out. Eventually, everything fades. A slow, quiet ending. This idea has a name: heat death, a universe that doesn't end with an explosion, but with silence. No light, no structure, no motion, just cold, empty space. It's simple, elegant, and possibly wrong. Because everything this prediction depends on assumes one thing: that the laws of physics never change. But what if they do? What if dark energy is not constant? Even a small change would alter everything. Now, this is where things become uncertain, because tiny differences in cosmic behavior can lead to completely different endings. For example, if dark energy grows stronger over time, the expansion accelerates faster and faster until eventually it overcomes everything. Galaxies are pulled apart, stars are stripped from their systems, planets drift into isolation. And in the extreme case, even atoms can no longer hold together. This is called the Big Rip, a universe where structure isn't lost slowly, but torn apart, from the largest scales to the smallest. Now imagine that, not darkness, but disintegration, reality itself coming undone. But there's another possibility. What if dark energy weakens or changes direction? Then expansion could slow down, eventually stop, and then reverse. The universe begins to contract. Galaxies move closer, temperatures rise, everything compresses into a dense state, a kind of mirror of the beginning. This is sometimes called the Big Crunch, an ending that looks like a beginning. But there's a third possibility, something even stranger. What if the universe doesn't end at all? What if it cycles, expanding, contracting, expanding again? An endless sequence, each cycle resetting conditions, possibly even altering the laws slightly each time. A universe not with one history, but many. Now pause here, because all of these futures depend on something we still don't understand: dark energy. Which brings us back again to the same unresolved question. What is driving the expansion of the universe, and more importantly, will it stay the same? Now connect this to everything we've explored. If the laws of physics can evolve, then the future is not fixed. It becomes conditional, dependent on how those laws change. And that means we cannot fully predict what happens next. Not because we lack data, but because the system itself may not be stable. Now think about that. For centuries, science has been about prediction, finding patterns and extending them into the future. But what if the patterns themselves can change? Then prediction becomes something else, not certainty, but possibility. Now, let's return again to our core questions. Why does expansion disagree? Maybe because it's not constant. How did galaxies form so early? Maybe because conditions were different. What is dark energy? Maybe it's not fixed at all. And now, a new question appears. What determines the fate of the universe? Because if the answer is changing laws, then the future is still open, still evolving. Now, here's where things become even more interesting. Some physicists have started to explore a more unusual idea. What if the universe has feedback, meaning what happens inside it can influence the rules themselves? Not directly, but gradually. For example, as matter forms structures, as galaxies cluster, as complexity increases, could that influence space-time? Could it subtly affect expansion? Over billions of years, small changes could accumulate, and suddenly, the universe is not just evolving in content, and it's evolving in behavior. Now, this idea is still speculative, but it introduces something powerful: the possibility that the universe is not just a system, but a process, not static, but adaptive. And if that's true, then the future of the universe is not something that simply happens, it's something that emerges. Now, let's step back again. We started with a mismatch in expansion, then we found early galaxies, then dark energy, then changing laws, then multiple universes, then emergent reality, and now we're questioning the future itself, not as a fixed outcome, but as an open system. This is where the third loop reaches forward, not just what is the universe, but what will it become? And here's the strange part. The deeper we go, the less certain everything becomes. Not because we know less, but because we're seeing more possibilities, more ways the universe could behave. And that leads us to the next step, because if the universe is evolving, then maybe it's doing something else as well, something we haven't fully considered yet. Because some physicists are beginning to ask a very unusual question. What if the universe is not just evolving, but processing? Processing information on a cosmic scale. And if that's true, then reality might not just be unfolding. It might be computing. What if the universe is not just evolving, but processing? Not just expanding, but computing. At first, this sounds like a metaphor, a poetic way to describe complexity. But some physicists mean it literally, because at the deepest level, physics doesn't describe things. It describes states and how those states change. Now think about that, a system moving up from one state to another, according to rules. That's exactly what computation is, a process that updates itself, step by step, moment by moment. Now pause here, because this reframes everything. The universe is no longer just a collection of objects. It becomes a system that is constantly updating. Now let's connect this to something familiar, a computer. Inside a computer, everything reduces to simple units, bits, zeros and ones, individually meaningless, but arranged in the right way, they create images, sound, entire worlds. Now imagine something similar on a cosmic scale. Instead of bits, we have quantum states. Instead of hardware, we have the laws of physics. And instead of a program, we have the evolution of the universe itself. Now, here's where it gets interesting. If the universe is processing information, then the laws of physics might not just describe behavior. They might be the rules of the computation. And if that's true, then changing laws means changing the computation. Which brings us back to everything we've been seeing, the expansion tension. Maybe it's not a contradiction, but a mismatch in how we interpret the rules. The early galaxies, maybe they formed differently, because the computation unfolded differently in that region. Dark energy, maybe it's not a force but a large-scale effect of how space processes information. And suddenly, all of our anomalies start to look like inconsistencies in a system we don't fully understand yet. Now, here's the deeper question. If the universe is computing, what is it computing? And the honest answer is, we don't know. It might not be computing something. It might simply be updating itself, evolving its own state without a goal. But some physicists suggest something more intriguing. What if the universe is optimizing, minimizing something, or maximizing something, like energy, or entropy. Now, entropy is often described as disorder, but more precisely, it's a measure of how many possible states a system can have, and the universe tends to move toward higher entropy. More possibilities, more configurations. Now, think about computation again, a system exploring its possible states. That sounds familiar. So one idea is this: the universe is exploring all possible configurations of itself, like a computation, running through possibilities. Now pause, because this connects to something we discussed earlier, the multiverse. What if each universe is not just a separate reality, but a different branch of a larger computation? Each one exploring different conditions, different rules, different outcomes. And our universe is just one path through that space. Now, let's go even deeper. If reality is information and the universe is processing it, then what we experience as time might not be what we think, not a flowing dimension, but a sequence of updates, one state after another, time as computation. Now, that changes something fundamental, because if time is just the order of updates, then the future is not already there. It hasn't happened yet. It is still being computed, which connects directly to what we explored earlier. The future is not fixed. It is unfolding. Now, let's bring back our questions again. Why does expansion disagree? Because we may be observing different parts of an evolving computation. How did galaxies form so early? Because computation may not proceed uniformly. What is dark energy? Possibly a large-scale effect of how the system updates itself. Are the laws of physics constant? Or are they rules that can evolve as the computation progresses? And now, a new question emerges. Is reality itself a kind of program? Now, before we go too far, there's an important distinction. This doesn't necessarily mean we are inside a simulation. That's a different idea. This is more subtle. It suggests that computation is not something happening inside the universe, it is the universe. Now, here's where things become even more intriguing. If the universe processes information, then there must be limits. Limits to how much information can exist, limits to how fast it can change. And physics already hints at this. The speed of light, a maximum rate of interaction, the Planck scale, a minimum unit of space and time. These might not just be physical limits, they might be computational limits. Resolution, update speed, like pixels, and frame rate. Now imagine that. Reality with a maximum resolution, a maximum refresh rate. Everything we see happening within those constraints. Now, this idea is still speculative, but it offers something powerful. A way to connect information, physics, and reality itself. Now, let's step back again. We started with a simple inconsistency, a number that didn't match, and now we're here. Considering that the universe might be a computational process, that space might emerge from connections, that laws might evolve, that reality itself might not be fundamental. And yet, even this doesn't answer the deepest question, because even if the universe is computing, we still don't know why. Why this system? Why these rules? Why anything at all? And in the next part, Yet we're going to move into the deepest question of all, not just about physics, but about existence itself. Because when you follow this path far enough, you arrive at something unavoidable, a question that sounds simple, but may never have a final answer. Why is there something instead of nothing? Why is there something instead of nothing? It sounds simple, but it may be the deepest question we can ever ask, because everything we've explored so far, expansion, galaxies, dark energy, laws of physics, even the possibility of a multiverse, all assume one thing, that existence itself is a given. But what if it isn't? What if the real mystery is not how the universe works, but why it exists at all? Now, at first, this feels like philosophy, something outside science. But interestingly, modern physics has started to approach it carefully, indirectly, through the structure of its own theories. Let's start with something familiar: empty space. We tend to think of it as nothing. But in physics, empty space is not empty. It's filled with fluctuations, tiny changes in energy, appearing and disappearing constantly, particles popping in and out of existence. This isn't speculation. It's been observed, measured. The vacuum is active. Now, here's the strange implication. If nothing is unstable, then maybe true nothingness doesn't exist, because even in the absence of matter, something still happens. Now, take that one step further. If the vacuum can fluctuate, could it produce something larger? Not just particles, but entire universes? Some physicists think so. The idea is that the universe might have emerged from a quantum fluctuation. Not from a cause in the traditional sense, but from instability. A system that cannot remain perfectly empty, giving rise to structure. Now, pause here, because this flips the question. Instead of asking, why is there something? We ask, why wouldn't there be? If nothingness is unstable, then existence might be inevitable. Now that sounds like an answer. But it raises another question. Why is the vacuum unstable? Why do fluctuations exist at all? Why do the rules allow anything to emerge? And now we're back to something deeper, because even if the universe arises naturally, it still depends on underlying rules, and those rules still need explaining. Now connect this back again to everything we've explored. We have a universe with very specific properties, specific constants, specific behaviors, and even small changes would make it completely different. Stars might not form, atoms might not hold together, life might never exist. And yet, here we are, in a universe that allows complexity, that allows structure, that allows awareness. Now, this leads to a powerful question. Is this coincidence or selection? In a multiverse, this could make sense. Many universes exist, each with different rules. And we happen to be in one where observers can exist. But if there is only one universe, then the question becomes sharper. Why these laws? Why this structure? Why this balance? Now, some physicists propose something radical, that the laws of physics are not arbitrary, but necessary, that there is only one consistent way for reality to exist. And what we observe is the only possible configuration, not one among many, but the only one that works. Now, that's a bold idea, because it suggests the universe could not have been different, that everything we see is not just what happened, beats, but what had to happen. But there's another possibility, equally strange. What if existence doesn't need a reason? What if the question why doesn't apply at this level? Because we're used to thinking in causes. This happens because of that. But at the deepest level, there may be no because, just existence. Now that idea can feel unsettling, because we want explanations, we want closure. But science has encountered this boundary before. In quantum mechanics, where events happen without clear causes. In cosmology, where time itself has a beginning. And now, in the question of existence itself. Now let's step back again. We started with a measurement problem, a disagreement in expansion. Then we found anomalies in galaxies, then dark energy, then the laws of physics, then multiple universes, then emergent reality, then computation, then the future. And now we're here, at the edge of explanation, where science meets its limits. This is where the third loop reaches its deepest point. Not just, what is the universe? Not even, how does it work? But, why is there anything at all? And here's the strange part. We may never fully answer that question, not because we lack intelligence, but because the question itself may not have an answer in the way we expect. Now, that doesn't mean the search ends. Now, in fact, it does the opposite. Because every time we reach a boundary like this, science transforms. It asks new questions, finds new ways to think, expands its own framework. And sometimes, those new questions lead to breakthroughs we couldn't have imagined before. So, where does that leave us? With uncertainty, but also with possibility. Because everything we've discovered so far has come from following questions, even when they led into the unknown. And right now, we are standing in one of those moments, a moment where the universe is revealing something deeper, not clearly, not completely, but enough to show us that our understanding is still evolving. And in the next part, we're going to bring everything together. Because there is one final perspective that connects all of this, from expansion to galaxies, to dark energy, to reality itself, a way of seeing the universe not as a problem to solve, but as something we are part of, and what that means. For everything we've been trying to understand, what if the universe is not something we observe, but something we are part of, not separate, not outside, but embedded within it? Because up until now, we've been treating the universe like an object, something out there, something we can measure, analyze, understand from a distance. But there's a problem with that idea. We are not outside the universe. We are inside it. Every observation we make, every measurement we record, every theory we build is happening from within the system itself. And that changes something fundamental, because it means we are not just studying the universe. We are part of the process by which the universe understands itself. Now pause here, because this idea shifts the perspective completely. The universe is no longer just matter and energy. It becomes something more. A system that includes observers, and those observers affect how reality is described. Now, this might sound abstract, But physics has already encountered this idea in quantum mechanics. At the smallest scales, the act of observation affects the outcome. Not because of something mystical, but because measurement is interaction, and interaction changes the system. So even at the most fundamental level, the observer cannot be fully separated from what is being observed. Now extend that idea to the entire universe. We are observers inside a system, trying to describe that system, and that creates a loop, a feedback loop, where the universe produces observers, and those observers produce models of the universe. Now, here's the deeper question. Do those models fully capture reality, or are they limited by our position inside it? Because we don't see the universe from the outside. We see it from one location, at one moment in time, under one set of conditions, and everything we infer is built from that perspective. Now connect this back to everything we've explored, the expansion tension we measure from here, but interpret as if we see everything, the early galaxies. We observe distant light and reconstruct a history we never directly experienced, dark energy. We infer its presence from effects we don't fully understand, and even the laws of physics. We assume they are universal because they appear consistent within what we can observe. But what if our perspective is only part of the story? Now, this leads to a subtle idea. What if reality is not just something that exists, but something that is described from within? Meaning, there may not be one single, complete description, but multiple perspectives, each valid within its context. Now, this doesn't mean anything goes. Physics still works. It still predicts. It still explains. But it suggests something deeper, that our models are not the final layer. They are approximations, maps of a reality we cannot fully step outside of. Now imagine that. Every theory we build is like a map drawn from inside the landscape. Useful, accurate, but never complete, because we can't see the entire terrain at once. Now, here's where things become even more interesting. If observers are part of the system, then their existence might not be accidental. It might be necessary. Some physicists suggest that the universe must be consistent with the existence of observers. Because without observers, there is no description, no measurement, no physics. Now that idea is controversial, but it raises a powerful possibility that the universe and observers are linked, not just by chance, but fundamentally. That reality includes both the system and the perspective. Now let's return again to our questions. Why does expansion disagree? Because we are interpreting from within a limited viewpoint. How did galaxies form so early? Because our reconstruction of history is incomplete. What is dark energy? Perhaps something that emerges from how we model the system. Are the laws of physics constant, or are they descriptions dependent on context? And now a new question forms. What does it mean to understand something that you are inside of? Because that is the challenge. We are trying to understand the whole from within it. And that may place limits on what we can know. Not absolute limits, but boundaries, edges of perspective. Now, this might feel discouraging, but it's not. Because every time we reach a boundary, we push it further. We develop new tools, new ideas, new ways of seeing, and gradually we expand what is possible to understand. Now, let's step back again. We started with a mismatch in expansion, and we followed it through deeper layers of reality until we arrived here, at a place where the question changes. Not just, what is the universe, but what does it mean to understand it? Because the universe is not just something we observe, it is something we are part of. And that means the story is not just about the cosmos, it is also about us, observers, participants, fragments of the universe. I'm trying to understand the whole. And in the next part, we're going to take one more step. Because there is one final way to see all of this, not as separate ideas, but as a single unfolding process, a story. And what that means for everything we've explored. What if the universe is not just a system, but a story, not written in words, but in events, in patterns, in the unfolding of time itself? Because when we step back from equations, from measurements, from models, what we are really observing is change, a sequence, a progression from one state to another. And that is the essence of a story, a beginning, a development, an unfolding. Now, this doesn't mean the universe has intention, or that not necessarily, but it does mean what we experience is not static, it evolves, and that evolution has structure. Now, think about everything we've explored. The early universe, simple, hot, dense, then expansion, cooling, particles forming, atoms, stars igniting, galaxies assembling, complexity increasing, eventually planets, chemistry, life, and now awareness. Observers, each step building on the last, each phase opening the possibility for the next. That's not random noise, it's a sequence, a progression. And when we look at it this way, the universe begins to feel less like an object and more like a process unfolding. Now, here's where this perspective becomes powerful, because it connects everything. The expansion of the universe that is not just motion, it's part of the unfolding. The formation of galaxies is not just structure, it's part of the development. Dark energy is not just a parameter, it's part of the dynamics. Even the anomalies we've seen, the tensions, the inconsistencies, may not be problems. They may be transitions, moments where the story shifts direction. Now, pause here. Because this changes how we interpret uncertainty. Instead of seeing it as failure, we can see it as incompleteness, not errors, but chapters we don't fully understand yet. Now, let's go deeper. In any story, the most interesting moments are the unexpected ones, the turning points, where something doesn't fit and everything changes. That's exactly where we are now, in cosmology. The expansion doesn't match predictions. Galaxies appear too early. Dark energy remains unexplained. The laws of physics may not be constant. Reality itself may be emergent. These are not small details. They are turning points. Now, here's the deeper question. If the universe is a story, what determines its direction? Is it purely physical, just equations unfolding? Or is there something about the structure of reality that naturally leads to increasing complexity? Because if we look closely, there is a pattern, from simplicity to complexity, from uniformity to structure, from particles to stars to galaxies to life to awareness. Now, this pattern is not smooth. It has disruptions, transitions, moments of instability, but the overall direction is clear. Now, some scientists describe this in terms of entropy, the universe moving toward more possible states, more ways things can exist, and within that, local pockets of complexity can form, like life, like intelligence, like us. Now, think about that. The universe creates conditions where it can observe itself, even if only briefly, even if only in certain regions, and that brings us back to the idea of observers. We are not separate from this story. We are part of it, a moment within it, a perspective through which the universe becomes aware of its own existence. Now, whether that awareness has deeper meaning is still unknown, but the fact that it exists at all is remarkable, because it means the story of the universe includes the capacity to reflect on itself. Now, let's return again to our questions. Why does expansion disagree? Because we are in the middle of the story, not at the end. How did galaxies form so early? Because early chapters may unfold differently. What is dark energy? Perhaps a driving force we don't yet understand. Are the laws of physics constant? Or do they evolve as the story unfolds? What is reality made of? It possibly not objects, but processes. And why does the universe exist, still unanswered? And now a new question appears. What is our role in this story? Because we are not just observers. We ask questions, we build models, we search for understanding, and in doing so, we become part of the unfolding itself. Now, this doesn't mean the universe depends on us, but it does mean the story includes us, that our perspective is one way the universe expresses itself. Now, let's step back again. We began with a small inconsistency, a mismatch in expansion, and we followed it through deeper layers until we arrived here, at a place where the universe is not just something to analyze, but something that unfolds, a process, a story, still incomplete, still evolving. And in the next part, we're going to take one more step, because there is one final question that brings everything together. If the universe is a story, who is telling it? And whether that question even has an answer. If the universe is a story, who is telling it? At first, this sounds like the wrong kind of question, because in science, we don't usually ask about storytellers. We ask about causes, mechanisms, equations. But sometimes, when you follow a line of thinking far enough, you arrive at questions that don't fit neatly into those categories, and this is one of them. Because if the universe unfolds like a story, with structure, with progression, with moments of transition, then it's natural to ask whether that unfolding has a source, not necessarily a creator, but something that gives rise to the structure itself. Now pause here, because there are a few different ways to approach this. The first is the simplest. No one is telling the story. It just happens. The universe evolves according to its rules, and what we perceive as structure is simply the result of those rules playing out, no intention, no direction, just process. Now, this view is consistent with physics. It doesn't require anything beyond what we already know. But it leaves something unanswered. Why does the process have this form? Why does it produce complexity? Why does it allow awareness? Now, the second possibility is more subtle. What if the story is not told by something separate, but emerges from the system itself, not imposed from the outside, but generated from within? In this view, there is no storyteller, because the universe is both the story and the process that creates it. Now think about that. A system that produces structure, and within that structure produces observers who then interpret that structure as a story. A loop, self-contained, self-referential. Now, this idea appears in several areas of science, in systems that organize themselves, in patterns that emerge from simple rules, in complexity arising from simplicity, and it suggests something interesting. That meaning is not imposed on the universe. It arises within it through the interaction of structure and awareness. Now, there is a third possibility, more difficult to define, more difficult to test, but impossible to ignore completely. What if the universe does have a deeper source? Not necessarily something we can measure, not something that appears in equations, but something that gives rise to the existence of the system itself. Now, science, by its nature, cannot directly address this, because science works with observations, with testable predictions, and anything beyond that falls outside its methods. But the question remains, not as a scientific hypothesis, but as a boundary, a point where explanation reaches its limit. Now, let's return again to everything we've explored. We began with a mismatch in expansion, a technical problem, a measurement that didn't agree. But as we followed it, it led us further and further into deeper questions about structure, about energy, about laws, about reality itself. And now, we're here, at a question that doesn't have a simple answer, not because we haven't found it yet, but because it may not exist in the way we expect. Now pause for a moment, because this is important. Reaching a boundary is not failure. It's progress. It shows us where our current understanding ends and where new ideas might begin. Now think about the history of science. Every major breakthrough started at a boundary like this, where something didn't make sense, where existing models failed, where questions became deeper, and instead of stopping, scientists kept going. They asked new questions, and they built new frameworks. They expanded what was possible to understand, and that is exactly where we are now, standing at the edge of what we know, looking into something that is not yet fully understood. Now, let's bring back our questions one more time. Why does expansion disagree? How did galaxies form so early? What is dark energy? Are the laws of physics constant? What is reality made of? Why does the universe exist? Zeus. And now one final question joins them. Is there a deeper origin to all of this? We don't have the answer, but the question itself is meaningful because it connects everything, from the smallest particles to the largest structures, from physics to philosophy, from observation to existence. Now, let's step back one more time. We began with a crack in our understanding, and we followed it through every layer of reality until we reached something deeper. Not a final answer, but a deeper awareness of how much there is still to explore. And in the next part, we're going to bring everything together, not as separate ideas, but as a single perspective, a way of seeing the universe that holds all of this without needing a final answer, and understanding why that might be enough. What if none of these mysteries are separate, not different problems, but different perspectives of the same underlying reality? Because along this journey, we've encountered many questions. Expansion doesn't match itself. Galaxies appear too early. Dark energy remains unknown. The laws of physics may not be constant. Reality may be emergent. The universe may be one of many. It may be computing. It may be evolving. And we may be part of it in ways we don't fully understand. At first, these feel like separate puzzles, independent mysteries. But what if they're not? What if they're all signs of the same deeper structure? Now, let's step back and look at the pattern. In every case, we expected something stable, a constant expansion rate, predictable structure formation, fixed laws of physics, a clear definition of reality. But instead, we found variation, mismatch, uncertainty, and most importantly, change. Now, pause here, because this suggests something simple but powerful. The universe may not be a static system. It may be a process, not something that is, but something that happens continuously. Now, if that's true, then everything we observe is part of that unfolding. Not fixed states, but moments within a larger evolution. And that changes how we interpret everything. The expansion of the universe is not just a number. It's part of the process. The formation of galaxies is not just structure. It's a phase of development. Dark energy is not just a parameter. It may be a feature of the unfolding itself. Even the laws of physics may not be absolute. They may be stable patterns within a changing system. Now imagine that, a universe where laws are not imposed, but emerge, where structure is not predetermined, but develops, where reality is not fixed, but evolving. Now, this perspective doesn't remove the mystery. It reframes it. Because instead of asking what is wrong with our model, we ask, what kind of system behaves like this? And the answer may be a dynamic one, a system that changes as it unfolds. Now let's return again to our core questions. Why does expansion disagree? Because we are measuring a moving process from different perspectives. How did galaxies form so early? Because the process allows rapid transitions under certain conditions. What is dark energy? Possibly a property of the process itself. Are the laws of physics constant, or are they patterns that remain stable until they don't? What is reality made of? Not just objects, but interactions, processes, relationships. And why does the universe exist? Still unanswered, but now framed differently. Not as a static question, but as part of an ongoing unfolding. Now, here's where everything connects. The anomalies we've seen, the tensions, the inconsistencies may not be errors. They may be signals, clues that we are seeing across layers, trying to describe a dynamic system with static models. Now, imagine trying to understand a river with a photograph. You capture its shape, but not its flow. You see where it is, but not where it's going. That may be what we're doing with the universe. Taking snapshots of something that is constantly changing. And when we compare those snapshots, they don't always align. Not because they're wrong, but because they're incomplete. And now this leads to a powerful shift. Instead of trying to force everything be into a single fixed model, we begin to think in terms of processes, evolution, transformation, and that opens a new direction. Because if the universe is a process, then understanding it is not about finding a final answer. It's about following the unfolding, observing how it changes, adapting our models as it evolves. Now let's step back one more time. We began with a small inconsistency, a mismatch in expansion, no? And we followed it through every layer of understanding until we arrived here, at a perspective where everything begins to connect, not perfectly, but enough to see the outline of something larger. And in the next part, we're going to take one final step, because there is one last shift in perspective, one that doesn't remove the mystery, but allows us to hold it, without needing a final answer, and understanding why that might be, exactly what makes the universe so compelling. What if the goal was never to fully understand the universe? Not completely, not finally, but to continuously explore it. Because after everything we've seen, every mystery, every contradiction, every unanswered question, we're left with something unexpected, not clarity, but depth, a deeper awareness of how complex reality really is. And strangely, that may be exactly what makes it meaningful. Now, pause here, because this is a shift. For most of history, we've thought of knowledge as something that removes mystery. You ask a question, you find an answer, the uncertainty disappears. But in modern physics, the opposite often happens. You find an answer, and the question becomes deeper, more precise, more difficult. And instead of closing the gap, it expands it. Now, think about our journey. We started with a simple mismatch, a number that didn't agree, and we followed it through expansion, through galaxies, through dark energy, through the laws of physics, through the nature of reality, until we arrived here, not with a solution, but with a new perspective that the universe is not something to be solved once and for all. It is something to be explored continuously. Now, this doesn't mean we stop searching for answers. It means we understand what answers are. Not final truths, but approximations, models that work within certain limits, and then evolve as we learn more. Now, here's the key realization. The uncertainty is not a flaw in our understanding. It is a feature of reality itself. Because a universe that is completely known would have no room for discovery, no room for curiosity, no room for growth. Now imagine that for a moment. A universe where everything is already explained, every law fixed, every question answered. It would be complete, but it would also be silent, static. There would be nothing left to explore, nothing left to wonder about. And in a strange way, that would be a smaller universe, not in size, but in possibility. Now compare that to the universe we actually inhabit, a universe with questions, with mysteries, with inconsistencies, with things that don't quite fit yet, a universe that invites exploration, that rewards curiosity, that evolves as we understand it. Now, this leads to a different way of thinking. Instead of asking, when will we finally understand everything? We ask, how far can understanding go? And what happens when we reach its limits? Because those limits are not the end. They are boundaries. And boundaries are where new ideas begin. Now, let's return one last time to our questions. Why does expansion disagree? Because our models are still evolving. How did galaxies form so early? Because reality allows possibilities we are only beginning to understand. What is dark energy? A name for something we haven't fully grasped. Are the laws of physics constant? Possibly not. What is reality made of? Still uncertain. Why does the universe exist? Still unanswered. And yet, despite all of this uncertainty, something remarkable remains true. The universe is understandable, not completely, but enough for us to explore it, to question it, to learn from it. Now, think about that. Out of all possible realities, we exist in one where understanding is possible, where patterns can be found, where questions can be asked, and not where answers can be approached, even if never fully reached. Now, here's the final shift. Instead of seeing mystery as something to eliminate, we begin to see it as something to engage with, something that gives meaning to the search itself. Because without mystery, there would be no curiosity, no discovery, no movement. Now, let's step back again. We began with a crack in our understanding, and we followed it until it became something else. Not a problem to fix, but a doorway into deeper questions, deeper perspectives, deeper awareness. And in the next part, we're going to take the final step. Not to find an answer, but to understand what it means to be part of all of this, and why that might be the most important realization of all. What does it mean to exist inside a universe like this? A universe that is vast, uncertain, constantly unfolding, and still not fully understood. Because after everything we've explored, this question becomes unavoidable. Not about physics, not about equations, but about perspective. Because we often think of ourselves as separate from the universe, small, insignificant, just observers looking out into something far larger. But that's not entirely true, because everything we are made of comes from the universe itself. Atoms formed in stars, elements created in extreme conditions long before the Earth existed, reassembled into something capable of awareness, something capable of asking questions. Now, pause here, because this changes something subtle, but important. You see, we are not outside the story. We are part of it, not just physically, but structurally. The same processes that formed galaxies also formed us. The same laws that govern stars also govern our existence, and now those processes have reached a point where they can reflect on themselves through us. Now think about that. The universe has become aware of itself. Not everywhere, not completely, but in small pockets, brief moments, and we are one of them. Now, this doesn't mean the universe has intention, but it does mean that awareness is part of what the universe does, just like forming stars, just like expanding, just like evolving. Now, let's connect this back to everything we've explored. The expansion tension, we question it. The early galaxies, we investigate them. Dark energy, we try to understand it. The laws of physics, we test their limits. And in doing all of this, we become part of the unfolding. Not separate observers, but participants. Now, here's the deeper realization of that understanding the universe is not just about knowledge, it's about relationship. How we connect to what we observe, how we interpret it, how we find meaning in it. Now, think about the scale of it all. Billions of galaxies, trillions of stars, distances so large that light takes billions of years to travel them. And yet, in one small corner, there is awareness, there is curiosity, there is the ability to ask, what is all of this? Now, that may not seem important on a cosmic scale, but it is. Because without that question, the universe would simply exist. With it, the universe becomes something else. Something that can be explored. Something that can be understood, even if only partially. Now, here's where everything comes together. All the mysteries we've followed are not just problems to solve. They are invitations. Invitations to look deeper, to question more carefully, to expand our understanding. And in doing so, can we become part of the process that reveals what the universe is. Now, let's return one last time to our questions. Why does expansion disagree? Because we are still learning. How did galaxies form so early? Because reality is richer than we expected. What is dark energy? Something we have yet to fully understand. Are the laws of physics constant? Possibly not. What is reality made of? Still unfolding. Why does the universe exist? Still unknown. And yet, despite all of that, something remains clear. We are part of it, not separate, not outside, but within. Now pause one more time. Because this is the shift. Instead of asking, what is the universe? We begin to ask, what does it mean to be part of it? And that question, well, it doesn't require a final answer. Because it's not just something we think about, it's something we experience every moment, through perception, through awareness, through existence itself. Now, let's step back one final time. We began with a small inconsistency, a crack in our understanding, and we followed it through every layer of reality until we arrived here at something deeper. Not an answer, but a realization that the universe is not just something to understand. It is something we are part of. And in the final part, we're going to close this journey, not with a conclusion, but with a perspective, a way of holding all of this together without needing it to be complete. And understanding why that might be, exactly what makes the universe so extraordinary. So, here we are. At the end of a journey that didn't really lead to an ending, but to something else, a different way of seeing. Because we started with a simple question or a mismatch, a number that didn't agree with itself, and we followed it. through expansion, through galaxies, through dark energy, through the laws of physics, through reality itself. And what we found was not a final answer, but a pattern, a realization of that the universe is far more subtle, far more dynamic, far more mysterious than we ever imagined. Now pause here, because if there is one thing this journey has shown us, it's this: the universe is not finished, not as a theory, not as a system, and maybe not even as a process. It is still unfolding, still revealing itself, still becoming something we don't fully understand yet, and neither are we. Because we are not separate from this story, we are part of it. The same universe that expanded from a hot, dense beginning is now sitting here, thinking about itself. Through you, through this moment, now think about that. Atoms forged in ancient stars, organized into a form that can ask questions about existence, that can wonder why anything exists at all, that can look out into the cosmos and feel both small and deeply connected. That is not a trivial thing. That is one of the most extraordinary outcomes of the entire universe. Now, we didn't solve everything. We didn't resolve the expansion tension. We didn't fully explain dark energy. We didn't uncover the ultimate nature of reality. And maybe that's exactly where we're supposed to be, because every answer we've ever found has led to new questions. Every boundary we've reached has opened into something deeper. And that pattern doesn't look like failure. It looks like exploration. Now, here's the final shift. Instead of asking, when will we finally understand everything? We can ask, what does it mean to be part of something that can be understood but never fully completed? Because that changes the feeling. It turns uncertainty from something uncomfortable into something alive, something open, something that invites curiosity. Now imagine a universe where everything was already known, every law fixed, every mystery solved, no questions left. It would be complete, but it would also be silent, static. There would be nothing left to explore, nothing left to discover, nothing left to wonder about. And in a strange way, that would be a smaller universe, not in size, but in possibility. Now, compare that to the universe we actually live in, a universe filled with questions, with mysteries, with things that don't quite fit yet. A universe that invites exploration, that rewards curiosity, that continues to unfold, moment by moment. Now, before you go, if this journey made you pause, even for a moment, if it made you see the universe just a little differently, take a second to like the video. And if you want to keep exploring ideas like this, the kind that don't just give answers, but change how you think about reality itself, consider subscribing, because there are still so many questions left, and we're going to keep following them. And if something in this video stayed with you, a thought, a question, a feeling, leave it in the comments, because sometimes the most interesting part of the journey is seeing how others are thinking about it too. And if you know someone who enjoys these kinds of ideas, share this with them, because the universe is a lot more interesting when we explore it together. And maybe the next question we ask will take us somewhere even deeper. Because if there's one thing we've learned, it's this: the universe doesn't end with an answer. It begins with a question.